Hello everyone, I'm Mauna Reddy Pishati. This presentation is part of my ee275 Advanced Computer Architecture coursework. I would like to thank my project advisor, Dr. Chanchu, for providing me with this opportunity to complete my project under his guidance. The motive behind this project was to learn the concepts of computer architecture, understand the flow of data and control, and enhance the Verilog coding skills. The goal of this project was to build a Neos2 architecture using Verilog and verifying by code of dot product and factorial. The first was the Neos1, which was a 16-bit architecture, and next to it is Neos2, which is 32-bit architecture. The Neos2 follows the traditional MIPS data path, but it has a different instruction set and a distinct instruction format. It is a soft-core processor. Hence, unlike the MIPS processor, the Neos2 does not depend on the fabrication. Rather, it can be implemented on any FPGA board belonging to Cyclone, Stratix, and etc. Now, in the R-type instruction, both the operands are taken from the internal register itself. These instructions can imply moving data between registers and arithmetic and logical operations as well. The I-type instruction is also called the immediate type instruction. The immediate field is used to provide the immediate offset, which can be an offset for memory location or an input for ALU operation. The various I-type instructions are differentiated on the basis of opcode as they are different for different instructions. The J-type instruction is used for jump operations. The immediate field provides the displacement offset to jump to the required location. The branch address generator adds this offset to the next address and comes up with a new address. This slide shows the Neos2 processor data path, and this processor data path is implemented in 5 stages. The first stage is the instruction fetch stage. Here the PC block acts as a pointer and points at a location in the instruction memory which holds the instruction. Initially, the PC is reset, so it points at a location 32-bit 0 where the first instruction is stored. The incrementer performs the task of incrementing the current address by a value of 4. The next location where the PC points is either the very next address in the memory location or a different branched address chosen by the PC source memory signal. The second stage is the instruction decode stage. Various modules in this stage are the instruction divide, register files, main control, and the sign extender. In the first stage of instruction decode, the instruction is divided and broken into instruction field in various subfields, such as opcode, OPX, RS, and immediate, and produces them as an output. The third stage is the execute stage. This stage generates the branch address, data memory address, results, and write back register address. The read data 1 from previous stage is directly fed to the ALU. The ALU either generates an address of data memory or a normal result. ALU also gives out a branch result when the comparison is done for branch operation. The ALU is capable of performing addition, subtraction, multiplication, comparison, and logical or operation as well. The fourth stage is the memory stage. The read and write operations related to memory are controlled by the read and memory write signals. The address from where the data is to be read is given by the ALU, where the data to be written is provided by the previous stage, read data 2. This stage also has the branch control block, which determines whether a branch is to be taken or not on the basis of the signals from the previous block. The last stage is the write back stage. This stage is the simplest one, which gives the address of register where data is to be written in case of R-type operation, the data that is to be written, and the generated branching address. The other very important block is the hazard detection module. This module basically is used to detect REW data dependency and give two control signals, which are stall and instruction flush. The data dependency occurs when read and write operations is done on same register. In such a scenario, this module pauses all the pipelines and allows the write back stage to complete its operation. This slide contains the benchmark program to test the dot product of two vectors. Register R2 is a pointer to vector A and register R3 is a pointer to vector B. Register R4 is used as a counter to loop iterations. The product of two vectors is stored in register 5 and the operation is iterated. In this slide, the table shows the pseudo instructions and the mapping risk instructions. The movia instruction is a complicated to implement as compared to the load word instruction. The movia is a pseudo instruction comprising of two different instructions, namely ORI and ORI, which in turn require two different forms of immediate offset value. Though complicated, the movia instructions was properly implemented. The benchmark program used to test the functionality included initial movia instruction to load the pointers and loop count before the loop starts. These, when coded in terms of ORI and ORI, caused several raw hazards. To deal with this initial hazard, the technique of rearranging the code was adopted. To deal with the raw hazard in later stages, the stall technique was used. This slide shows the screenshot of the instruction ORI and which is fetched and decoded R2 as targeted register with immediate value. The instruction here shows that this slide consists of a screenshot where the instructions were reordered to avoid dependency in pre-loop operation, where most of the move operations were performed. The first three operations are ORI, which basically generates zeros, so they are not marked. From the markings, it can be seen that the instruction for ORI is fetched. It is decoded, giving out R2 as register RT and immediate value as R2 hexadecimal 4, which is a location of the first element of vector A. In execute stage, the ALU generates the memory location address, that is 32 hexadecimal 4. In memory location, this value is carried forward. Now, in the screenshot, we can see that the pointer for vector A and B is loaded in the respective registers as per the test program. The register R4 is first cleared, then loaded with the count value, that is 6. It can be seen that as there is a raw dependency between clearing R4 and loading 6 into it, so there is a stall. In this screenshot, as per the program and test data, the first element of vector A, that is 1, is loaded in register R6, and the first element from vector B, that is 6, is loaded in register R7. The loaded data is multiplied and stored in register R8. The writing operation is actually a register write back signal, which is high. Now, in this screenshot, you can see that the resultant product is added with contents of R5 register and stored in it. The registers R2 and R3 are incremented by 4. The registers R4 is decremented by 1. In this screenshot, you can see that the register R6 is loaded with second element of vector A, that is 2, and the register R7 is loaded with the second element of vector B, that is 5. Now this loaded data is multiplied and stored in register R8. The first branch instruction is executed and PC value jumps from 44 to 20. And this slide shows that next two elements of vector A and B are loaded in R6 and R7 registers, and the loaded elements are multiplied and stored in R8. The contents of register R8 are added with those of register R5 and stored in register R5. Now, as the expected result of dot product. As per the test data, the final dot product is 56, that is 38 hexadecimal. Now the same final result has to be stored in register R5 in our execution result in hexadecimal format. As the loop count is 0, there is no branch and the final result is written in memory location 32 hexadecimal 38 of data memory, which is the next free memory location. This is followed by the execution of branch instruction, that is stop. So this way we have successfully implemented the dot product of two vectors. Now coming to the benchmark program for the factorial. The benchmark program for factorial, we have used movia instructions as shown in the slide for the first two slides. And next we have reconstructed the code using ORI and ORI instructions, as you can see in the slides. Now, as per the screenshot, the instructions were reordered to avoid dependency in preloop operations where most of the move operations were performed. The first operation is ORI, which basically operates 0 so that it is not marked. From the markings, it can be seen that the instructions for ORI is fetched. The value of n is equals to 3 for factorial is stored in R4. The register R4 is first cleared, then loaded with the count, that is 3. It can be seen that there is a raw dependency between clearing R4 and loading 3 in it. So there is a stall. So in the screenshot, we can see that as register R2 is initially loaded with 1, the value of read data will be initialized to 1. And the jump instruction has the value of the return address stored in the register R1, which stores the value of the return address of the subroutine. But the instruction JR31 register and the subroutine is not called and executed correctly. The program is being abruptly terminated. Therefore, the result of the program is the value of register R2, which is 1, is shown in the figure below. Now in this slide, you can see that after getting 1 stored in register 2, program is being terminated. Now the value of 3 factorial is computed and it is stored as the value 6 is, the result 6 is stored in the at the 32 hexadecimal 6 location. Now this way we have successfully implemented our factorial using our Neos 2 architecture. Now the future scope of this can be the stalls in branching can be reduced further if the branch unit can be moved to a previous stage. Additional cache memory and data forwarding unit can be implemented, and ALU can be improvised to include more number of operations. Data and instruction memory can be enlarged for more data storage. Thank you.